Smart grids are for stupid people. Smart grids have emerged in the past 2 decades in many developed nations. The United States, United Kingdom, many countries of Europe, Australia. In this talk, we explore why smart grids are a very stupid idea from a national scale cyber-physical systems security perspective. This is Robert Hendon, one of the key experts in grid security. Electrical grid network infrastructure suppliers are making mistakes that have already been made by credit card companies. These corporations do not understand the risks, nor have the corporate culture of security developed in other internet technology sectors. Over 40% of the 2012 incidents were energy related is documented by the Department of Homeland Security in the United States. The risks of a smart grid are undoubtedly higher than traditional systems security problems. Mr. Hendon is right, and problems have only been increasing from there. US politicians are allocating millions of dollars in an aggressive effort to study the security of cyber-physical systems that comprise the United States grid and other critical infrastructure. Inspiration for this measure comes from the December 2015 attack on Ukraine. I am sure you are all familiar with this. 250,000 citizens were left in the dark by an attack that has been attributed by most to Russia. Industrial control systems in 3 separate power generation facilities were attacked in a coordinated fashion. It involved snooping on a lot of network traffic. It actually took a lot of resources in order to effect this attack. US politicians acknowledge that the outage could have been much worse if Ukraine had been using smart grid technology instead of the dumb technology it presently uses to run its grid. Stupid is simply safer. During the past 15 years, over 2.4 trillion, not million, not billion, $2.4 trillion has been invested into renewable energy and smart grid improvements. Renewable energy is a government-enforced farce that is a pretext for destroying the infrastructure and economics of developed nations' energy markets. These investments have largely occurred in countries such as the USA, England, Australia, Denmark, Spain, and Germany. The economic destruction wrought by these investments is estimated to be some 10 times worse than the sum total damage caused by Chernobyl. Ukrainians, please do not commit this error. Claims have been made extensively by environmentalists that spreading renewable resources across large geographical areas will average out the power available from these resources. This is a false claim. We can see very clearly that increases in wind power in Germany correspond to the same wind power increases in Spain. There is no way to get around the need that increasing amounts of renewable energy deployments have for larger amounts of energy storage, responsive generation, and improved electrical grid infrastructure. To make the wind turbines and solar panels in Germany and Italy and Spain work, they require large amounts of infrastructure connecting them to pumped hydroelectric facilities in Norway and other Scandinavian countries. Renewable energy means larger areas of control and influence for the grid. All these systems are known as smart grid technology. Okay, these are examples of smart grid technology. You have such systems as mechanically switched capacitors, thyristor switched capacitors, thyristor controlled reactors, and this device, which would be along a power line, this is known as a power flow controller. All of these smart grid systems will affect the power available at different points in the grid, different substations, or the power that is flowing along the lines. Whereas before, in a dumb grid, I simply had a power plant next to a town. As the town needed more energy, the grid would just detect it, the power plant would detect this, increase its output by measuring the signals local to the power plant, okay? Such smart grid systems instead are integrated into what is known as wide area distributed control systems. These interact over the internet with sensors, protective relays, and these flexible AC transmission systems. This is a quote: "The influence of FACS devices, FACTS, flexible AC transmission systems, are not confined to one bus or line. Changing the voltage at a certain bus or the power flow on a line also modifies the voltages and power flows of the surrounding grid. Thus, if one could compromise a FACS system, you might be able to destabilize regional areas of the electrical grid through the dynamic interactions inherent to these devices." These interactions are extremely difficult to model and predict. Thus, it is difficult to generate the control laws for the control systems of FACS devices. A single model cannot cover problems involving transients that happen on the microsecond scale, as well as power plant stability issues that happen on the order of 10 seconds. A single computer model might be able to look at a line fault that happened in the order of hundreds of microseconds, but this same program cannot also be used to model how one power plant might interact with the generator of another power plant hundreds of kilometers away. There are no integrated models available for these systems yet. We are deploying these systems, and the models by which we understand the behavior of these systems is still effectively cutting-edge research. We're going blindly into uncharted mathematical territory. Dumb grid control structure is hierarchical. Each controller utilizes its own local measurements only. Each control area utilizes measurements in its own utility area only, and has its own SCADA system, supervisory command and data acquisition. Relay protection is pre-programmed to protect individual pieces of equipment and rarely requires digitally networked communications. There is no online coordination between different regions within a large interconnection as long as you don't deploy smart grid technology. As long as conditions are normal, the industry is quoted as saying, "There is no need for regional scheduling of resources, nor for region scale or national scale coordination of generation. The control is entirely hierarchical and quite effective." Smart grids change this stable structure to less stable structures. Managing distributed control systems in future power grids will require immense frameworks of automatically reconfigurable control systems, as both the structure of the grid, the needs of the customers, and the system operating conditions change. I need to have, for the smart grid, a computer control system that is composed of many thousands of sensors located over the internet, that is comprised of multiple controllers and multiply actuated devices, such as the flexible AC transmission systems and generators themselves. How do I keep such a system secure? So let's look at some of the effects. So, oh, that's not animated. This animation codes the frequency shift of the grid, and you can see in Oklahoma, in the Midwestern United States, it is a key area where large amounts of wind generation resources are deployed. You would see that as the wind availability increased and decreased, the fluctuations in this area are naturally stronger than those of more traditional grids around it. So I would say that mathematically, the area of Oklahoma is destabilizing itself and requires compensation from the surrounding grid. These instabilities exist, and this is very important, on the order of 0.1 to 10 hertz. The grid is always oscillating around its ideal 60 hertz operating frequency, or as is the case in Europe, 50 hertz. Okay. If I were to take one of these generators and somehow modify its output, one generator purposely fluctuating its output on an order of magnitude of 1 hertz has been shown to destabilize a regional grid within 20 seconds. So you can actually track the destabilization of the grid. Grids with large amounts of renewable integration and natural gas turbines are over twice as vulnerable to destabilization as those dominated by large steam turbines, such as from coal and nuclear power plants. Daily, there are significant declines in frequency on the eastern United States interconnection due to the loss of one or more generating units. These generation units, for whatever reason, they disconnect to the grid. Maybe a squirrel gets on a transmission line, a raccoon jumps on the contactor at a substation. Many things can happen, even in these very reliable grid systems. So within several seconds of such an event, the power system will settle down to a new lower frequency and establish a new equilibrium frequency. We note the megawatts of generation required to induce such a frequency change. A parameter called beta, which is the ratio of the power lost to the frequency change, is calculated from these events. The average of this parameter has been dropping from 1994 to 2009 in the American grid. So I can see that the American grid is 50% as stable as it was 20 years ago. We can calculate the fact that our grid is becoming more vulnerable to potential instabilities. So, what might an attacker do using these natural instabilities? Let's imagine an attacker opens and closes a relay on a substation, and they are doing this twice per second. This will cause the generator within 25 miles of that substation to speed up and slow down, and then speed up and slow down until its frequency becomes so great that it trips its automated protection mechanisms and disconnects itself from the grid. If I were to drive a number of these generators off the grid in such a way, I would have wide-scale blackouts. If I were to disable the protective systems of these generators, I might destroy the generators or associated transmission equipment, and large transformers in America currently are not produced in America anymore. If you were to take out certain very large transformer equipment in America, sections of the grid may be down for 6 months or more while replacements are ordered from China. If you can manage to destroy or permanently disable grid equipment, estimates above 10 million lives lost are in fact published by the Department of Homeland Security. These are very serious issues, and we're very lucky that people have not been exploiting these things in America on such a large scale. So there's a vulnerability. How might a computer hacker or just some electrical engineer exploit this vulnerability? Okay. One of the key pieces of equipment associated with smart grids is known as the phasor measurement unit. A phasor measurement unit is located at certain points along the grid, and it is measuring the alternating current waveforms. If anyone, this is going to be some difficult explanation. So I have a voltage and a current waveform, right? Alternating current, all right? I might be able at any point to measure the difference between the voltage and the current, but imagine I am trying to determine what is the difference between the voltage and the current hundreds of miles distant, okay? The time lag associated with taking that measurement means that I cannot measure it here and send them somewhere to compare. I do not know at what true instance in time that measurement occurred. Phaser measurement units are synchronized by a global positioning system clock. So a measurement is created combining the GPS signal and the analog input from the voltage and current measurements, and they are compared to actually let me know where in the waveform I am at each of these points. So if I am measuring at the generator, I might say if this is the reference phase angle of 0, and then a transformer some 20 miles away is at 0 plus 1 degree, then I would know that power is flowing from the substation, or from the generator to the substation in the direction of increasing phase angle. This is extremely important data that is used to determine how I might turn a switched capacitor bank on and off, or change the impedance of a line with a power flow controller to actively manage how power is flowing around the grid, especially in those grids that have large amounts of wind and solar resources. So if I was an attacker and I wanted to say, I want to screw with the GPS radios of some phaser measurement units, how would I know which substation has the phaser measurement unit? So this is actually pretty simple. You'll look at the substation, you'll see both current instrument transformers and voltage potential instrument transformers. Both of these have the large insulators, the big bars that have the rings around them that isolates the voltage of the line from the ground. At the top of a current transformer, I have the current carrying conductor surrounded by a very large transformer coil that couples the current from the line down into the measurement unit. And then in the potential transformer, I'm actually isolating the current carrying conductor, and I am taking a very small line down to a step-down transformer that reduces that very high voltage to one that I can measure. Okay? So identifying the phaser measurement unit says I need to see 3 current transformers and 3 voltage transformers as instrument transformers. Whenever I see them together, I will know that a phaser measurement unit is active at this substation. I don't need to go in the substation or break into it physically. In fact, you'll see that it's very easy to fool these systems to give them a wrong phase measurement. Right? It's not difficult to find in general where the phaser measurement units are in America. In fact, this is published information. You can just get it online wherever you want. If one were to overlay this map with a slightly more confidential diagram of the transmission grid infrastructure, like overlay this data on top of where are the power lines, where are the generators, where are the wind turbines, you could plan a very effective attack. In fact, I can see that wind energy is clustered up here in Kansas and down in Oklahoma, and I have a lot of phaser measurement units deployed there to accurately measure what is the power flow doing in these areas of unstable resources. I also have a lot of connection in the Western Interconnect where I am measuring the phase of the load sources along the coast, and then I am using those to control certain hydroelectric and other generating systems that are located far more inland. Power flowing across long distances needs this information in order for me to stabilize it. Okay? So, how hard is it in fact to spoof a GPS signal? It has been used to hack Pokemon Go. The power signals in GPS radios are extremely low. You don't even have to know how GPS radio works in order to perform this. Radios are in fact extremely low cost due to the fact that they are low power, and the GPS receivers are extremely sensitive, so you can absolutely overload them with a signal. Okay, so how might such an attack proceed? I would identify all phase measurement units within a target region. Spoofing only one phase measurement unit is likely going to appear to the ISO operator as a sensor fluke, and thus the control system would understand to disregard that phase measurement unit synchrophasor signal. Okay? 2, I'd locate GPS radio signal spoofers of sufficient power such that you are hitting all your target locations with at least minus 135 decibel watts. This is 2 orders of magnitude above the nominal received GPS signal strength of minus 155 decibel watts. A 20 decibel noise floor drowns out all other GPS signals as background noise. You could very easily cover a 200-mile radius area with one drone broadcasting with 500 milliwatts or more of signal strength. Okay? 3, my radio would detect and synchronize with the existing GPS satellite data. 4, I would begin broadcasting my own stronger GPS signal, making sure that I don't cause any sudden changing in the timing signal that is part of that GPS signal, so that the phase lock oscillators do not detect an immediate phase shift. In each of these phase measurement units, sometimes it is understood that the GPS signal will skip sometimes, okay? So in the GPS time calculator, there is a phase lock loop operating at the expected 60 hertz. And if there are any sudden deviations, the phase measurement unit understands to trust its own prediction of the measurement more than what it is actually measuring. So it is very important to maintain a consistency in the timing signal so that the phase measurement unit does not lock out its GPS signal, its GPS signal measurement, okay? Then finally, once you have gotten these systems to trust your new timing signal, your broadcasting, you can shift the degree sensed by any phasor measurement unit by changing the timing signal by 46.1 microseconds per degree. Okay, so if I can change the measured phase angle, like what would I then do with this ability to lie to the grid about its measured phase angle? Once you've established control over local phasor measurement unit time synchronization, you can simulate resonances that energy systems typically have already. The automatically controlled generators in that region will respond to this sensor input and cause actual power flow resonance on the grid. So the automated systems that would respond to a detected decrease in power flow over here suddenly and say, I must increase my output in order to compensate for this lack over here, would in fact, at the same frequency that I am lying to them about what disturbance is I am creating, would create a disturbance. So the grid operator will not know where the problem is coming from, because the automated control systems of the grid would create the same problem that you were lying to them that is there, okay? Remember, typical resonances used to destabilize generators will be within an order of magnitude of 1 hertz. If you want to understand more specifically the kinds of resonances that correspond to different areas of the grid, you should Google subsynchronous resonance and torsional interaction of generators. Higher frequency interactions typically correspond to smaller generating regions, while lower frequency interactions tend to correspond to large generators that are separated by large distance. I mean, this makes sense inherently, right? Longer wavelengths, lower frequencies, right? Okay, good. 3 minutes?
Yeah.
Really?
For a break.
Oh, for a break. Oh. All right. Yeah, good. Don't get too greedy with phase shifting. Any attack coordinator would need to generate a believable transition of phase states. This is the measured phase signal that would come from a phasor measurement unit. So a measurement like this is believable. I might say that, I just a generator started to increase and then got cut out from the grid. That is a believable shift. But here, this is a fluke. The system naturally knows to discard garbage measurements. Or, if I suddenly just jam the GPS signal, it will default into a safe control state. You need to believably fool the smart grid sensors. A lot of people have tried to build a variety of algorithms based around throwing out simply erroneous data that is not generated by a human hacker. There are no systems. There are not Gaussian filters. There are not any kind of filter systems that an intelligent attacker could not make believable to the grid. Okay? Utilities have multiple ways to collect these time signals that PMUs require, and no grid operating entity is as yet only using synchrophaser technology for mission-critical operations. If PMU data were cut off because of a hacking attack, operators would have the older data analysis and models to drive observers, computer models that guess what the grid is actually doing. Attacks such as the Iranian drone capture using GPS spoofing and the recent attacks by the North Koreans jamming South Korean GPS signals have awakened operators to these issues, and thus they are prepared for simple jamming attacks, just loss of the signal. I recommend reading Meeting PMU Data Quality Requirements for Mission Critical Applications by Anurag Srivastava. Okay. After this, we'll take a break. This is a simulation of what would happen if I were to supply believable incorrect data to phaser measurement units. This is the result of what the system thinks is happening, and this is what is actually happening. And basically, the system, observing the increased power flow and thinking the voltage is dropping, inserts a shunt capacitor bank, driving the voltage even higher until I have to end up shedding loads and cutting off generators. Okay? This attack assumed that the protective relays on substations and generating equipment were still operational. If those systems were not allowed to disconnect from the grid and were to continue to increase their output, you would have started arcing across transmission lines or terminals of transformers at substations, or overheating bearings of generators and destroying this equipment, disabling them permanently. Backup protections are designed, you might say that the security of the grid, because it was not designed for cybersecurity, at least it was designed for redundant failure. The grid, the local devices on the grid still have their own protection. If you were able to change the phaser measurement unit data and cause the grid to act in a dangerous way and also disable the protective relays, you would cause permanent damage to keep things shut down for months at a time. Okay, Rick.
Question?
Yeah,
maybe I missed something. Why do we need to measure the best coordinates all the time?
Okay, so it is not for the location data, it is for the time signal. Inside of the GPS signal is a nanosecond accurate clock. And so, I need a whiteboard to draw this. So imagine I have the AC waveform, right? At one point, I might say it is doing like this, okay? But maybe at different points along the grid, like point A, I am here, point B, I am here, and point C, I am here, right? How do I know where in that waveform I am at the same instance in time, but geographically separated? Yes?
Yeah, do you see any ways like how to really protect those?
What?
Within that case. But can you propose any like ideas how to protect the system from hacking? Do you see any ways how to protect this like system from hacking?
Okay, so this is interesting. You saw the scale of investment that had been put into the smart grid now. We're going to explore some in a second as to like why this is so dysfunctional. None of these systems were designed when security was an issue. And as Robert Hendon was quoted in the beginning, none of the companies are even thinking about these kinds of issues until up about 2 to 3 years ago, okay? So the dummies are in charge. I can say that because I'm in Ukraine. Don't send this to American friends. But how would I protect this? So like, you can't. Like, so let's imagine that they made all of these systems cyber secure. You still cannot change how GPS satellite works, right? How do I deal with the fact that I need to have one satellite signal covering an entire area? There's no kind of authentication protection that you can do. There's nothing you can do. This is a sensor that is operating on entirely unauthenticated input. You would have to somehow put atomic clocks at every substation to observe like true time. And this is a scale of a problem that it will not work. When you have something depending on a non-authenticated signal that is easily overridden by children that are playing Pokemon Go with a software-defined radio that costs like $50. I mean, there's really no good way to get around it except to cut the smarts out of the grid. I mean, this is the title of the article, you know, US legislators are considering dumbing down the grid to prevent attacks. If you try to make integrated distributed control systems that rely on unauthenticated signals, I mean, someone could detect that you were broadcasting. You were not allowed to broadcast in the GPS band, right? But how will somebody know unless you start broadcasting? So you are broadcasting, then maybe they can detect where that signal is, triangulate it, and shut you down within a couple hours, but you only need 5 minutes in order to affect a severe power quality problem on the grid, to shut off and damage large grid equipment. If you've done your homework, right? If I've gone in, I've compromised all the supervisory command and data acquisition, and I've turned off all the protective relays, I can suddenly take over the phaser measurement unit synchronization signal and wreak whatever kind of havoc I want. And especially in grids like the United States and Europe, where large numbers of these are deployed, hundreds of billions of dollars would have to be sent somehow changing the way this equipment fundamentally operates. I don't know if people are even looking at this problem yet, which is stupid because we know, like Iran, you know, they lied to the drone and they made the United States drone think it was in a landing zone and it just lands. I mean, can you encrypt the GPS signal? Maybe. I'm actually not a computer expert at all. I'm a power systems engineer. I don't even like computers.
Okay, so like let's imagine like if we could like do something like NSA tracking on all the power grids that actually do this like smart and stuff.
Yeah.
Could we do that? And like in case hackers start say hacking something, they just Also, why there is nothing in Nebraska? I mean, just wondering.
I mean, you need to synchronize corn. No. Corn grows regardless of what time of day it is. It needs sunlight. This is good.
Okay, so like the question is like, couldn't like NSA do something like tracking on all those like smart grids in order to prevent this stuff?
The resources required to do this, right? I mean, these people can't even stop 9/11. How are they going to like stop? So you saw like recently people are already probing the American grid. Within the past couple years, people have been taking pot shots at transformers and different things connected to the grid. If I'm able to disrupt a signal and do it 100 miles remote from where that measurement unit is with a sufficient power device, or just within a kilometer in an extremely low power device that would likely not be detectable.
So what you're saying, it just takes a lot of resources, right?
Right. I mean, I guess the argument is that we've stabbed ourselves in the stomach, and so everyone's like, oh, I'll just put more Band-Aids on that. I mean, you should stop stabbing yourself in the stomach. I mean, Band-Aids, for security companies, I mean, if you manufacture Band-Aids, I mean, by all means, support smart grid. It makes a lot of work.
So, period.
Thanks.
Okay, so some more traditionally IT-related methods of attacking the smart grid. Compromising smart grid distributed control systems is rarely difficult. The key problem for attackers is knowing what to modify once gaining access. The security of the hierarchical grid is still largely in place at a lower level, even though you might have integration layered on top of it. At some point, the computer hacker requires a power systems engineer and a control systems engineer in order to understand how the weak cybersecurity can be leveraged to obtain the desired physical result in the cyber-physical system. Think about the kinds of attacks we've already discussed. I'm inducing some kind of resonance from 1/10 of a hertz to 10 hertz, depending on the scale of the grid I'm attacking. Think about these types of attacks the next time you drive by a sewage lift pump, a transformer, a solar panel, or a wind turbine. These are all potential backdoors into much larger critical infrastructures. There have been many times that people have found security vulnerabilities in solar inverters on unsecured home wireless networks, just driving through neighborhoods. And a lot of these systems will have virtual private network access back into the vendor of this system that they use for collecting data. And then you have access to thousands, hundreds of such systems, which can quickly add up to megawatts of power distributed within a local grid. If you're commanding more than 5% of the generation in a given grid area, you're going to be able to cause serious damage. Whether you're getting in to the substation through a local transformer in the network, or you're getting in through renewable energy systems, there's a variety of access points to get past firewalls and into the SCADA networks associated with grid systems. Okay, so in general, you're going to start off with finding protective equipment and either increasing the delays or somehow freezing them into standby mode to prevent the disconnection of grid equipment upon detection of overvoltage, undervoltage, overfrequency conditions. Then you're going to try to make some sensor or some actual source of generation change a virtual output or change its actual output to cause damage with the prior disabled protective devices not stopping the damage to their respective systems. So any kind of Google source will show you thousands of articles about how different home solar systems, how wind farms, the most popular Vestas V148H wind turbine, because you are distributing all of these systems, you're making you're making a large number of access points available to get into critical infrastructure on the grid. All these are, again, designed by people that do not know how internet technology is secured. Smart meters, smart inverters, smart transformers are all typically not even going to be monitored in residential and urban areas. So when you're looking for educating yourself on protocols, such things as Goose, the General Object-Oriented Substation Event Protocol, or Modbus, the modular bus, both developed back in the 1980s, are going to provide you access and control to systems that will allow you to generate resonant conditions similar to the PMU attack and disable protective relays. Combinations of attacks where I might lie to grid sensors and tell them there is increasing power available through increasing local phase margins, combined with a sudden loss of local distributed real energy sources, would cause low voltage conditions and brownouts and blackouts. Alternatively, sending grid sensors false information telling them that more power is available, combined with decreasing local generators, would cause overvoltage conditions. This could potentially cause arcing between different lines. You can cause lines to sag, break, and you can destroy equipment at substations. If any of you are familiar with Shodan, you can scan, look for Modbus systems available online. Look at port 502. You're going to find over 12,000 of these systems easily accessible. You'll see them associated with the names of common vendors such as ABB, Siemens, and any of the plethora of home solar inverter manufacturers. Several protocols used to transmit message between SCADA components that are of key importance to us are TASE.2, T-A-S-E. Look up IEC 61850 protocols such as MMA and Goose. Also searching for the Modbus port 502, or looking up the DNP and DNP3 ports will educate yourself about what is typically available by these systems. Again, Goose is especially relevant as it is the standard protocol used to define the time settings of protective relays for substation equipment. So substations, I might go in and, understanding the Goose protocol, tell a substation that an event is happening that it should trip off a relay, or I could go in and disable or change the timing settings on those relays to prevent them from performing their proper function. One of the largest protocols used by the smart grid is DNP3. It's based on the IEC 61850. It is the key protocol for attacking fax systems and other smart grid equipment. Research into this protocol reveals increasing numbers of gaping holes in its security since 2013. An excellent paper from DNP Security clearly lays out the data structure of DNP3 and multiple methods of attacking it. This is a great quote here. As most smart grid technology was developed by those with no comprehension of IT security, security was not part of the design of the DNP3 protocol and similar protocols. DNP3 specifically does not include any authentication or encryption technologies in its structure. And actually, DNP3 recommends not to use authentication capabilities in order to improve the ability of slave units to respond to any command by a master on their network. So it's like, these are people who are like, please don't put passwords on this. It might make the equipment hiccup. Okay. So some of the specific attack scenarios that we could go into to compromise the security of SCADA systems and their networks. An intruder could use a protocol analyzer tool such as Ethereal or other well-known techniques to intercept DNP3 frames. You could then, using the published available description of what's in these frames, determine which is a master and what slaves it's communicating with. You're grabbing the unencrypted plain text frames. You don't have to decrypt these or anything, okay? The intruder then used the unencrypted data frames to contain control and settings information in subsequent attacks on the SCADA system or on the intelligent equipment devices that are slaves to the SCADA master over the internet. Such attacks could take the form of shutting off the master software and then replacing it, or you could take the remote units and I could basically put them under denial of service conditions. I can put them under loops or other standby conditions. In addition, the intruder could change the settings on the master or the slaves such that the equipment fails to operate when it should, causing bus line and transformer damage, or operating when it shouldn't, again causing service interruption. So there's plenty of tools, like let's imagine that I go and I hack into my local transformer and I want to map out what is connected to my local substation. I can get in and use available programs such as Semantic 7 or Phoenix Modbus, and I can get onto the Modbus network by just plugging into the serial connection available at a local transformer. I can then use Python scripts such as Modbus Discover that basically runs through all potential 256 addresses on that Modbus and maps out what's on that network. I then get a lot of data back from that network that will allow me to say, you know, if this device on my substation has 2 timing settings, then I know that this is one certain kind of relay. If I know that I have a signal available to me that generates 3 different events, I know that I'm dealing with some kind of a 3-phase relay. So understanding the nature of the kind of equipment connected to a substation will allow me to specifically modify its function, or if you don't want to bother with that, you can simply plug in and just shut down that SCADA network by flooding it with traffic. The structure of Modbus networks is such that the master sends out a request for information or some function from one of its slaves, and then the network holds until that specific slave sends back its either an error response or the requested information or confirmation is performed as function. So if I just flood that Modbus network with bad requests, it freezes. Remember, disable protective devices, then hacking into generating sources or some kind of switching equipment that would change the power flow in the grid, induce resonances between 0.1 to 10 hertz depending on the size of the grid attacked. Right? So, in summary, Western governments are heavily investing into test beds to look at all possible system interactions, such as in Canada. There's a big smart microgrid university they're building now. They're failing even in this because small, smart microgrids don't capture the dynamics of what would happen on large grid infrastructure. Okay? So grids with long transmission line distances and synchronization requirements still don't have the right kind of areas for us to do the kind of research needed to validate the security of these systems before they're deployed. You need a real grid to deploy these systems in order to test their resilience to real grid attacks. Creating models of these cyber physical systems that incorporate the power grid dynamics as well as the cyber security vulnerabilities are on the cutting edge research still, for those of you interested in entrepreneurial opportunities. Consistent policy failures such as these continue in the tradition of the World Bank and IMF leading developed nations into wasting trillions of dollars of wealth. Thankfully, the Ukraine has gotten an immunization to the madness of the smart grid. Perhaps the suffering of last December will prevent your politicians from leaving your country open to much greater suffering in the future. The only safe electrical grid has its control systems disconnected from the internet with deadly force limiting access to all computers, sensors, and actuated equipment. All patriots and noble citizens take note of these truths. Do not commit the engineering sins that the U.S. has done. Be smart and keep your grid stupid.
The question is, question, but it's hard enough. So we have like this system with a network. So any guy who's smart enough to stall $50 in a bar, don't get caught, buy equipment, he has a phone, he can hack any substance, hack this part, state, I don't know, all electric in this region, or hack your home, sand battery, or what it's called, and what to do. It's like you say, anyone possibly can do this, but what to do from this point we get now? We can't make us network stupid because we're reflected to it. We already use this, and we can't like go back to when it was stupid. So what to do?
So the question is, how smart do I need to be? What kind of decisions am I making based on the information I have available? If I'm trying to integrate resources across long distances, so imagine I have a generation area like in Oklahoma, and I have generators in Dallas, Texas, 350 miles away, that are trying to respond to the actions of those wind turbines. I necessarily have to make that generator dependent on signals it's receiving through the internet. Whereas before I made my grid forcefully integrate those renewable energy systems, that generator simply had sensors on its own stator that were detecting the actual voltages and currents local to it, that it then governed its output based off of those signals. That is very easy to secure, right? That's a Modbus network within one building that no one has physical access to, right? It is behind multiple layers of barbed wire fence. So to say, like, if I want to monitor the network so I have a better situational awareness so that a human operator can make a decision based on that data, that is much more secure. It's not flawless, but that's the normal state of how modern dumb grids are operating. But to say I'm going to automate the response of generators and flexible AC transmission systems based on computerized distributed control systems that require large numbers of inputs from a variety of devices, from a variety of vendors, this becomes an intractable security problem. So like what do we do? What do we do now? Recycle the wind turbines and turn them into steam turbines. Melt the steel down. Use the concrete for gravel in roads. I don't know. It's a huge waste of money. Really, what you can do, you can not waste more money in the future. Build nuclear power plants. Those are very stable and safe. Modern ones.
Just like that, the question: if not a smart grid, then why actually any grid? Why not just? I understand some of the downsides of it, of course, but but this idea has been around for many years.
Mm-hmm.
Why not make or purchase or I don't know get a home scale nuclear reactor and just put it in every house? So if one is hacked, then the others are not dependent.
This is a good question. It's also a security issue. To have many is very close to the city. It can measure the demands of the load and respond to that with electrical signals at the power plant. If I am physically separating the generation facility from the loads or coordinating generators across distances of more than maybe 200 kilometers, I must have the kind of networked infrastructure that smart grid requires. So really, it's a problem of saying, what is the right kind of generation to have? We knew this back in the 1960s. We knew this back in the 1970s. It is only when we started trying to integrate beyond the scale of what we knew was a workable solution in order to make way for things like wind and solar that we started seeing these instabilities, that we started making ourselves open to cyber security problems.
We should have revived Tesla, which invented the wireless transmission of electricity.
No, the air, this is a very high impedance medium. You're not going to drive a large amount of current through air, even at giant frequencies. I would say that regional nuclear power is the ideal solution. I know Chernobyl happened in Ukraine. This was not a good thing. Modern nuclear plants are not like this in any way.
Even Japan has failed with...
This is good question. How many people died from radiation in
I
Fukushima?
have no idea. There is no research that has been regarding the effect, how radiation affects.
Officially is 0. 0 people dying.
Say it loud, say it proud.
0.
0!
Maybe some old baby. No?
How
No.
many people die in Kazakhstan?
Okay, I actually know. I agree.
Done.
I have a question. Thank you for your interesting presentation. If you were to advise the government of Ukraine on the cybersecurity strategy to protect its strategic energy grids, what would be the top 3 things that they could do, given that they have a very limited funding that they're working with?
So the lowest cost solution presently available, I have a grid, okay? Regionally, I have the power consumption throughout the day. The purpose of the grid is to meet the load, okay? I have the base load demand, which will be so many megawatts of consumption, and then I will have the variable loading throughout the day based on, when people are turning on the heaters in the winter at night, or maybe they are turning on the air conditioning in the day during the summer, the lights are on during the day. Many things contribute to variability in the grid, okay? I should build a baseload generator, which is coal or nuclear, and then gas turbines will respond to the demand changes throughout the grid. The algorithms for determining how to do this are established as early as the 1920s. This is a solved problem that does not need any additional solution. The original, like a generator that has an embedded system, a control circuit that cannot be reconfigured, that responds within a certain stable region, like the controls of this generator are just able to respond to loads between this and this. And that's all you need. And there is no vulnerability of this system. You'd have to like drop thermite bombs, or like maybe you can blow up the power plant and that will shut the grid down, but it is simply not vulnerable to cyber attacks. It makes no sense that the World Bank and the IMF would push developed nations to make their grids more vulnerable. It's like paying someone millions of dollars to put a bomb under your bed where you sleep at night, and then like you leave the trigger like under a rug on the sidewalk, and you're just waiting for someone to step on it. There is no justifiable reason other than the fact that renewable energy results in huge amounts of subsidies. Companies like Tesla, the corporate welfare whore of Elon Musk, has made huge amounts of money from the stupidity of politicians that believed his lies that green energy is somehow beneficial for reducing carbon emissions. Wind and solar do not effectively reduce carbon emissions. You look at a country like France, they built out nuclear power in the 1980s, they reduced the carbon emissions. The most secure kind of a computer is one that is off. Right? I'm not a computer scientist. I'm an electrical engineer. I don't want more computers. Smartphones are bad enough. Okay. Any more?
What is the time precision needed for fast measuring units? What is the time precision needed for fast measuring units?
What is the time precision needed for fast metering units?
Yes.
Okay. The phase measurement units, right? The phase of the grid in the US is 60 hertz. This means that every 16.7 milliseconds, I am going through a full cycle, correct? I say that full cycle is comprised of 360 degrees, right? All the way around the circle, or one sinusoid. Okay, in a typical grid, like a regional grid on the Eastern Interconnect, I will have, let us say that the reference angle of the grid at the generators is 0 degrees. At the farthest load away from the grid, the phase angle might have increased to 25 to 30 degrees. Okay? Every degree corresponds to 46.1 microseconds. Okay? So 1 degree might correspond to 2 to 5% of an actual reasonable power flow rate. So you're talking about needing to be accurate within microseconds. It is impossible, for this reason, it's impossible to synchronize phasor measurement units by them sampling a signal and then somehow comparing them at a third location. The inaccuracies in when I might sample that signal and the latency in transmitting that data over the internet far overshadow the accuracy required. This is why when the sampling event is initiated, the timestamp from the GPU signal or the GPS signal is recorded. And then that data might be just transmitted once every 10 seconds to a central grid operator, right? Like, the data is not necessarily needed immediately, but what is the data must be computed accurately. Is this make sense? Seti?